The Australian craton is some of the oldest rock on Earth, 2 billion years old. It survived ice ages, supercontinent cycles, and extinction events that killed 96% of all life. And on April 4th, 2026, at 4:30 in the morning, it shook hard enough to wake tourists sleeping near Uluru. That is not supposed to happen. The nearest plate boundary is 3,000 kilometers away. There is no active fault system. There is no volcanic activity. There is just ancient, cold, dead rock that has been sitting there since before complex life existed. Except now it is not sitting there anymore, and the timing of what happened in space 36 hours earlier is the part of this story that nobody can explain away, not even the people who want to. If stories like this keep you watching the way they keep me digging, make sure to hit like and subscribe to the Skylab so you do not miss the next update as this unfolds in real time. Drop a comment with where you are tuning in from, what time it is there, and whether you think the sun had anything to do with what happened under Uluru. Now let's get into it. Part 1. The quake that shouldn't exist. On April 4th, 2026, at exactly 1826 Universal Time, a seismograph station in the middle of the Australian outback registered something that made no immediate sense. The needle jumped, not at a plate boundary, not along a subduction zone, not anywhere near a fault system that geologists monitor with any regularity. It jumped in one of the most geologically quiet places on the face of the Earth, 77 kilometres south-southwest of a tiny service town called Uluru, in the Northern Territory of Australia. If that name doesn't ring a bell, the landmark next to it will. Uluru exists for one reason. It is the gateway to Uluru, Ayers Rock. That enormous monolith of red sandstone sitting in the middle of the Australian desert, sacred to the Anangu Aboriginal people, photographed by millions of tourists and embedded in the cultural memory of an entire continent. The rock that looks like it was dropped there by something ancient and unknowable, because in a sense, it was. Uluru is the exposed tip of a geological formation that extends kilometres beneath the surface, made of Arcos sandstone that was deposited roughly 550 million years ago during the Cambrian period. And on the morning of April 5th local time, at approximately 4:30 am, the ground near that rock shook hard enough to wake people from a dead sleep. Think about what it means to be woken by an earthquake in a place like this. You're in the middle of the Australian outback, one of the most remote locations on the planet. The nearest major city, Adelaide, is more than 1,500 kilometres to the south. Darwin is about the same distance to the north. You came here to see a rock formation that has stood unchanged since before dinosaurs existed. And now, the ground beneath your hotel bed is vibrating in a way that the ground in this region almost never vibrates. Guess at the sails. In the Desert Hotel, a resort that sits just outside Uluru National Park, were jolted awake by the tremor. One guest reported that nothing fell off the bookshelves, which sounds reassuring until you realise that the shaking was felt across a radius of hundreds of kilometres. Reports came in from communities scattered across the Central Australian desert, from people who had never felt an earthquake before and assumed something had hit their building. That kind of reach, from a magnitude 5.5 earthquake, tells you something about the rock it travelled through. Cold, ancient, impossibly hard cratonic crust transmits seismic waves with brutal efficiency. This is one of the counterintuitive things about earthquakes in stable continental interiors. A moderate earthquake in a place like California might be felt within a radius of 100 kilometres because the warm, fractured rock near the plate boundary absorbs and scatters the seismic energy. The same magnitude earthquake in a craton can be felt 5 or 10 times farther away. The energy doesn't get absorbed the way it does in the soft, warm, fractured rock near plate boundaries. The ancient cratonic rock is dense and cold and continuous, and it acts like a bell. Hit it and it rings. The energy just goes, it travels, and people feel it a very long way from where it started. This is why the 1988 Tennant Creek sequence was felt across most of the Northern Territory, and why the Uluru event woke people up hundreds of kilometres from the epicentre. The rock itself amplifies the reach. Now here's where the numbers start to get interesting. The United States Geological Survey recorded this event at magnitude 5.5. That is already notable for this location. But the European Mediterranean Seismological Centre, the EMSC, recorded it at magnitude 6.0 using body wave magnitude. That is a significant discrepancy. A half magnitude difference on the Richter scale does not mean the earthquake was 10% bigger. It means it released approximately 5.6 times more energy. If the EMSC number holds, this event moves from notable to historic, one of the most powerful earthquakes ever instrumentally recorded in the deep interior of the Australian continent. The depth was 10 kilometres. That is shallow. A shallow crustal event in a region where the crust has been stable for billions of years. The USGS issued a green pager alert, which means the probability of casualties and economic loss was low. And it was low because almost nobody lives out there. Central Australia is one of the most sparsely populated regions on the planet. The nearest significant population centre, Alice Springs, sits roughly 350 kilometres to the northeast. There was no tsunami, because this happened in the middle of a continent, 1,000 kilometres from the nearest coastline. To give you a sense of scale, the Canberra Times compared this event to the 1989 Newcastle earthquake, which was roughly the same magnitude. That Newcastle event killed 13 people and damaged an estimated 50,000 buildings. The difference was population density. Newcastle is a city. The land around Uluru is one of the emptiest inhabited places on the planet. The earthquake's energy was the same. The consequences were entirely different because almost nobody was there to experience them. But the significance of this earthquake has nothing to do with damage. It has nothing to do with casualties. It has everything to do with where it happened and when it happened. Because this was not a normal earthquake. This did not occur along a known fault system at a plate boundary, where the physics of stress accumulation and release are well understood. This occurred in the interior of a craton, a geological term for the ancient cold, thick core of a continental plate. A mass of rock so old and so stable that it has survived every tectonic upheaval the planet has thrown at it for more than 2 billion years. The question that seismologists will be working on for months is straightforward. What made it move? The tectonic loading is real. The Australian plate is being pushed from all directions by boundary forces thousands of kilometres away. But that stress has been accumulating for millennia. Why did the fault fail on this specific day, at this specific hour? Every earthquake has a cause. At plate boundaries, the cause is obvious. Plates push against each other, stress builds, the fault slips. The physics is textbook. But in the interior of a craton, the cause is a genuine scientific puzzle. The stress is there, yes, accumulating slowly from distant plate boundaries. But that stress has been accumulating for thousands, maybe millions of years. The fault has been sitting there, loaded, for an inconceivable amount of time. So when it finally fails, on this specific day, at this specific hour, you have to ask yourself what changed. What was different about April 4th, 2026 compared to the millions of days before it when the fault held? And that brings us to the detail that changes this story from a geological curiosity into something much bigger. Because 36 hours before this earthquake struck, something hit the Earth's magnetic field with enough force to light up the sky across multiple continents. A geomagnetic storm, a G2, moderate on the scale. And a team of researchers at Kyoto University published a paper just 2 months ago that describes, in physical detail, exactly how a geomagnetic storm could reach down through the atmosphere and into the crust and push a fault over the edge. That is where this story's going. And by the time we get there, you are going to see this earthquake in a completely different light than you do right now. Because this is not just a story about a tremor in the outback. This is a story about whether the sun can shake the Earth. Whether something 93 million miles away can reach through the vacuum of space, through the magnetosphere, through the ionosphere, through the atmosphere, and into the crust of this planet and move rock that has been sitting still for 1 billion years. And the timing is either an extraordinary coincidence or a piece of evidence that the scientific community is going to be arguing about for years. Stick with me, because this goes deeper than anyone is talking about. Part 2. The oldest rock on Earth just moved. To understand why a magnitude 5.5 earthquake near Uluru matters more than a magnitude 6 or even 7 at a plate boundary, you need to understand what a craton is and why the Australian one is special. A craton is the ancient core of a continental plate. It is the part that has survived everything. While the edges of continents have been built up, torn apart, subducted, recycled and reassembled over billions of years of plate tectonics, the craton just sits there. It is cold, it is thick, it is extraordinarily rigid. The lithosphere beneath a craton can extend 250 kilometers or more into the mantle, far deeper than the lithosphere beneath younger continental crust or oceanic plates. This depth and coldness make it resistant to deformation. Cratons are, in the most literal geological sense, the most stable pieces of the Earth's surface. The Australian craton is Archean age. That means the rock at its core formed more than 2.5 billion years ago, during an era when the Earth's atmosphere had almost no oxygen, when the only life was microbial, when the planet's surface looked nothing like what we know today. Some of the mineral grains in the Western Australian craton, the Yilgarn and Pilbara blocks, have been dated to more than 4 billion years, making them among the oldest surviving pieces of the Earth's original crust. To put that in perspective, the Earth itself is approximately 4.54 billion years old. These rocks formed when the planet was still cooling, still organising itself, still figuring out what it was going to become. They predate the first oxygen in the atmosphere by over 1 billion years. They predate multicellular life by roughly 3 billion years. They have been sitting there, quiet and cold and incredibly dense, through everything this planet has endured. This is the rock that just moved. Let that sink in for a moment. The Indo-Australian plate, which carries the Australian continent, is moving northeast at approximately 7 centimetres per year. That makes it one of the fastest moving continental plates on the planet. It is being driven by a combination of slab pull from the subducting edge of the plate beneath Indonesia and ridge push from the southeast Indian ridge far to the south. These forces generate compressive stress throughout the continental interior, even though the interior is thousands of kilometres from the boundaries where the stress originates. The nearest subduction zone to Uluru is the Sunda Trench, roughly 3,000 kilometres to the north, where the Indo-Australian plate dives beneath the Eurasian plate and creates the volcanic arc of Indonesia. The nearest divergent boundary, the southeast Indian ridge, lies more than 3,000 kilometres to the south. In between, there is nothing but continent. Old, cold, stable continent. So where does an earthquake come from in a place like this? The answer lies in the ancient scars hidden beneath the surface. When continents formed and broke apart and reformed over billions of years, they left behind fault structures, zones of weakness within otherwise rigid rock. These faults are not active in the way that the San Andreas Fault is active, where slip occurs regularly and the recurrence intervals can be estimated within decades. Cratonic faults may go hundreds of thousands of years between movements. Some may go millions of years. The stress accumulates over immense timescales, transmitted slowly from the distant plate boundaries, loading these ancient structures incrementally, millimetre by millimetre, century by century, until something causes them to fail, and that is the part that makes intraplate earthquakes so much more mysterious than their plate boundary counterparts. At a subduction zone, the physics is relatively straightforward. You have two plates converging. Stress builds along the interface. When the friction is overcome, the fault slips, the energy is released, and the cycle begins again. The fault geometry is mapped. The recurrence intervals can be estimated. The triggering mechanism is understood. None of that applies in the interior of a craton. And this is what makes intraplate seismology one of the most frustrating and most fascinating subdisciplines in all of Earth science. You're trying to understand events that happen rarely, on faults you cannot see, driven by forces that are difficult to measure, in rock that gives you almost no information about its recent history, because nothing has happened there recently by any human definition of the word. The fault that ruptured near Uluru on April 4th may have been there for 1 billion years. It may not be mapped. The recurrence interval could be anything from 10,000 to 10 million years, and the question of what caused it to fail at this specific moment, after holding together for an inconceivable stretch of time, is genuinely and maddeningly open. Geologists can tell you that the fault was loaded. They can tell you that the Indo-Australian plate was pushing. They can tell you that the stress was sufficient for failure. What they cannot tell you is what made it happen on April 4th instead of April 5th or March 15th, or some random Tuesday in 2031. The tectonic loading provides the background stress. But background stress has been there for millennia. Something has to play the role of the trigger. Something has to be the last straw. The contrast with plate boundaries is stark and worth emphasizing. Japan experiences hundreds of earthquakes per year that are stronger than what just happened near Uluru. Chile, Indonesia, the west coast of the Americas, all of these regions shake constantly and people barely notice. The infrastructure is built for it. The public is accustomed to it. The science is mature enough that forecasts and hazard models exist. Central Australia has none of that. The building codes are not designed for seismic loading. The public has no experience with earthquakes, and the science is playing catch-up with every event, because the events are so rare that the dataset is tiny. Every significant earthquake in the Australian interior is both a data point and a surprise. Geoscience Australia records approximately 100 earthquakes of magnitude 3 or larger across the continent per year. Events of magnitude 5 or above in the deep continental interior happen perhaps once every 2 to 5 years. Events of 5.5 or above in the cratonic heartland, more than 1,000 kilometres from any plate boundary, are significantly rarer. This is not a common occurrence. This is the kind of event that gets a dedicated paragraph in the annual seismic review. And the question that a growing number of researchers are asking is whether the trigger for events like this can come from above rather than below. Whether what happens in the ionosphere, 93 million miles from the Sun, can reach down through the atmosphere and into fractured rock and determine the moment that a billion-year-old fault finally gives way. And something has to play the role of the trigger. Something has to be the last straw. In geological terms, the trigger could be anything that changes the stress state on the fault by even a tiny amount. The tidal pull of the moon, a change in groundwater pressure, the weight of sediment deposited by a river over thousands of years, or, as a team at Kyoto University now proposes, an electric field generated by a geomagnetic storm that penetrates the crust from above. Because 36 hours before the ground moved near Uluru, the ionosphere was on fire. Part 3. The 36-hour question. Alright, let us rewind the clock 36 hours from the moment the ground shook near Uluru and look at what was happening above our heads. Because this is where the story pivots from geology to astrophysics, and the connection between the two is the entire reason we are here. On April 3rd, 2026, Earth's magnetic field took a hit. The KP index, which measures geomagnetic disturbance on a scale of 0 to 9, reached 6.67 at 1800 UTC. That is a G2 event on the NOAA geomagnetic storm scale. Moderate. Not the worst the Sun can throw at us, but not subtle either. A G2 storm means voltage irregularities in power systems at high latitudes, the kind of subtle fluctuations that grid operators have to actively compensate for to prevent cascading failures. It means increased drag on low Earth orbit satellites as the upper atmosphere heats and expands, slowing spacecraft and altering their orbits. It means the aurora borealis becomes visible at latitudes where people don't normally see it, dipping down into the northern United States and across northern Europe. If you were in Minnesota or Wisconsin on the night of April 3rd and you looked north, there is a decent chance you saw green curtains of light dancing across the sky. Beautiful, yes. But that beauty is the visible signature of charged particles from the Sun slamming into atmospheric molecules, transferring energy, and rearranging the electrical architecture of the upper atmosphere. The storm did not come from nowhere. Geomagnetic storms never do. Every storm has a solar source, a specific event or series of events on the Sun that launched the material or the magnetic disturbance that eventually reached Earth. And the source of this particular storm is important because it connects to a chain of solar activity that has been building for over a week. This storm was the product of two overlapping solar events that arrived at Earth within hours of each other, combining their effects like two waves meeting in the ocean. And the combination was worse than either one alone. The first was a coronal mass ejection, a CME, that had left the Sun on April 1st. If you're not familiar with CMEs, think of them as the Sun throwing a chunk of itself into space. A coronal mass ejection is a massive expulsion of magnetized plasma from the solar corona, the Sun's outer atmosphere. They can contain billions of tons of material and travel at speeds ranging from a few hundred to several thousand kilometers per second. When one is aimed at Earth, it arrives in 1 to 4 days. This particular CME was generated by active region 4405, which had produced an X1.4 solar flare on March 30th. An X-class flare is the most powerful category on the solar flare classification scale. The scale goes A, B, C, M, X, with each letter representing a 10-fold increase in energy output. An X1.4 is a serious event, the kind that produces radio blackouts over an entire hemisphere and has the potential to launch a substantial CME, The X-1.4 launched a wall of magnetized plasma into the solar wind, and 3 days later, that wall arrived at Earth. On its own, the CME would have produced a notable geomagnetic disturbance, but it didn't arrive alone. On April 2nd, a coronal hole high-speed stream reached Earth as well. Coronal holes are regions on the Sun where the magnetic field opens up and allows solar wind to escape at elevated speeds. This particular coronal hole had a negative magnetic polarity, which is significant because when the magnetic field of the incoming solar wind is oriented opposite to Earth's magnetic field, the coupling is much more efficient. The energy transfer from the solar wind into the magnetosphere is maximized. It is the difference between pushing a door that is latched and pushing a door that is already ajar. Think of it like this. If the CME was a truck hitting Earth's magnetic field head-on, the coronal hole high-speed stream was a sustained gale force wind that had already been pushing on the field for hours before the truck arrived. The field was already stressed, already flexed, and then the CME hit it while it was in that compromised state. The result was a storm that was more intense and more sustained than either event would have produced on its own. The combination of the CME and the coronal hole high-speed stream produced 3 consecutive 3-hour periods of elevated geomagnetic activity on April 3rd. The KP index registered 6.67 from 1500 to 1800 UTC, then 5.67 from 1800 to 2100 UTC, then 5.67 again from 2100 UTC on April 3rd through midnight into April 4th. By early April 4th, the KP reached 5, which is a G1- storm, and NOAA's Space Weather Prediction Center issued Alert ALTK 05. The geomagnetic field then gradually settled over the following 18 hours. Now track the timeline. The G2 storm peaked at 1800 UTC on April 3rd. The earthquake near Uluru struck at 1826 UTC on April 4th. That is approximately 36 hours. 36 hours. That number sits in the exact center of a window that has appeared repeatedly in the scientific literature. Multiple independent studies over the past 2 decades have identified a 24 to 72-hour period of elevated seismic probability following intense geomagnetic activity. The window is not precise because the proposed mechanism is not a simple cause and effect chain. It is more like a probability shift, a loading of the dice, and the Uluru earthquake fell right in the middle of it. The solar wind data surrounding this event fills in the picture. At the time of the earthquake, the solar wind speed was 574 km per second, declining from approximately 650 km per second at the storm's peak. That is fast. Normal solar wind cruises at 300 to 400 km per second. The elevated speed was driven by the waning coronal hole high-speed stream. The electron flux tells another part of the story. The 2 megaelectron-volt electron flux had been continuously elevated above 1,000 particle flux units since April 3rd at 0920 UTC. On April 4th, it peaked at 4,465 particle flux units. These are the electrons that cause satellite charging, the ones that build up on spacecraft surfaces and discharge in ways that can damage electronics. But in the context of the Kyoto model, the elevated particle environment is a marker of the ionospheric disturbance that the model proposes can penetrate the crust. Now, I want to be very clear about something before we go any further. Presenting a timeline like this is not the same as proving a connection. Events happen all the time. If you look hard enough, you can find temporal correlations between almost anything and almost anything else. The human brain is a pattern-matching machine, and it will find patterns where none exist. That is why we have statistics. That is why we have controlled studies. That is why the phrase correlation does not equal causation exists. Here is the part that makes this more than just a temporal coincidence. Correlation is not causation. Every scientist worth listening to will tell you that. 2 things happening close together in time does not mean one caused the other. Billions of things happen simultaneously on any given day. The human brain is wired to see patterns, and most of those patterns are illusions. But when a team of researchers at one of the most respected universities in the world publishes a paper describing a physical mechanism by which event A can cause event B, and then events A and B happen in the exact sequence and within the exact time window that the paper predicts, the conversation shifts. It stops being about correlation and starts being about whether the mechanism is real. That paper was published in February 2026, 2 months ago. The team is at Kyoto University in Japan, which is not some obscure institution. Kyoto University is one of the top research universities in Asia and is consistently ranked among the best in the world. The paper was published in a peer-reviewed journal, meaning other scientists reviewed the methodology, the data, and the conclusions before it was allowed into the scientific literature. This is not a blog post. This is not a YouTube theory. This is a formal academic contribution from credentialed researchers at a world-class institution. And their model does something that no previous attempt at linking solar activity to earthquakes has done. It describes, in quantitative physical terms, exactly how the energy gets from the ionosphere into the crust. Not hand-waving, not vague correlations, actual physics, actual numbers, actual testable predictions. Part 4. The Kyoto Model. We have now established the timeline. G2 storm peaks on April 3rd. Earthquake strikes near Uluru on April 4th, 36 hours later. The temporal correlation exists. The question is whether there is a physical mechanism that can turn that correlation into something more meaningful. And for decades, the answer from mainstream science was a flat no. For decades, the idea that the sun could influence earthquakes was treated as fringe science at best, pseudoscience at worst. It lived in the same neighbourhood as claims about the full moon causing madness or planetary alignments triggering disasters. The mainstream geophysical community dismissed it, and for understandable reasons. The energy scales don't obviously match. The sun is 93 million miles away. Earthquakes involve the release of energy stored in rock under pressure. The connection is not intuitive, but science moves forward when someone finds a mechanism that makes the non-intuitive make sense. And in February 2026, 3 researchers at Kyoto University did exactly that. Takuya Mizuno, Shengrui Kao, and Ken Umeno published a paper proposing what they call a capacitive coupling model for solar seismic interaction. The name is technical, but the concept, once you break it down, is surprisingly elegant. Start with what we know. The Earth has layers. At the top, you have the ionosphere, a region of the upper atmosphere between roughly 60 and 1,000 kilometers altitude, where solar radiation strips electrons from atoms, creating a layer of electrically charged particles. Below that, you have the neutral atmosphere. Below that, the crust. The Kyoto team proposes that these 3 layers act like a giant capacitor. If you remember anything from high school physics, a capacitor is a device that stores electrical energy between 2 conducting surfaces separated by an insulating layer. The ionosphere is one conductor, the crust is the other. The neutral atmosphere in between is the insulator. When the ionosphere is disturbed, as it is during a geomagnetic storm, the electrical balance of this system shifts. Now here is where it gets interesting. The crust is not a uniform slab of rock. It is full of fractures, faults, and cracks. And in many of these fractured zones, especially at depth, you find water. Not liquid water, in the way you think of it. Water at extremely high temperatures and pressures, sometimes in a supercritical state, where it exists as a fluid that is neither liquid nor gas but something in between, with unique electrical properties. These water-filled fractured zones, the Kyoto team argues, can act as capacitors themselves, embedded within the larger ionosphere-atmosphere crust capacitor system. When a geomagnetic storm hits, the total electron content of the ionosphere increases dramatically. Increases of several tens of TeC units, which stands for total electron content units, have been documented during major storms. This shift in the ionospheric charge state propagates downward through capacitive coupling. The atmosphere does not conduct electricity well, but it does not need to. In a capacitor, charge does not flow through the insulator. The electric field propagates through it. Think of it like holding a phone charger near a piece of metal. You do not need to touch the metal to induce a current. The electromagnetic field does the work across the gap. Scale that up to the size of a planet, and you have the basic principle the Kyoto team is describing. The ionosphere is the charger, the crust is the metal, the atmosphere is the gap. And the geomagnetic storm is the moment you plug the charger in. According to the Kyoto team's calculations, this propagation can generate intense electric fields inside microscopic voids within fractured rock at seismogenic depths. The resulting electrostatic pressure can approach several megapascals. Now, a megapascal might not mean much to you as a number, so let me put it in context. The tidal stresses that the moon exerts on the Earth's crust, The gentle gravitational tugging that causes the solid Earth to flex slightly as the Moon orbits are on the order of kilopascals. A kilopascal is 1,000th of a megapascal. Some studies have already linked even these tiny tidal stresses to earthquake triggering, finding small but statistically significant correlations between tidal forces and seismic activity. The ionospheric perturbation proposed by the Kyoto model could, under the right conditions, produce pressures that are 1,000 times larger than the tidal forces that are already suspected of influencing faults. That is not a subtle effect, that is a hammer compared to a feather. And here is the key distinction that separates the Kyoto model from every previous attempt to link solar activity to earthquakes. The model does not claim that geomagnetic storms cause earthquakes. That is an important word, cause. The model claims that geomagnetic storms can act as a secondary trigger on faults that are already at or very near critical stress. The fault has to be loaded. The tectonic forces have to have brought it to the breaking point over centuries or millennia of slow accumulation. The geomagnetic perturbation does not create the stress. It tips the balance. It is the last straw. The geological equivalent of the final grain of sand that causes the pile to avalanche. Think of it this way. Imagine a parking lot full of cars, all with slightly different fuel levels. The Kyoto model is not proposing that the geomagnetic storm fills the gas tanks. It is proposing that the storm turns all the ignition keys at once. Only the cars that already had fuel will start. But the ones that start at the same time, driven by the same external event. This distinction matters enormously because it explains why the connection does not show up as an 11-year cycle in earthquake statistics, which is the primary objection that the USGS and other institutional bodies have raised. If the sun caused earthquakes, the argument goes, we should see more earthquakes during solar maximum and fewer during solar minimum, following the 11-year solar cycle. We do not see that pattern. Therefore, the sun does not cause earthquakes. The Kyoto model explains why the cyclical signature is absent. The secondary trigger mechanism only works on faults that are already at critical stress. The number of faults at critical stress at any given moment is determined by tectonic forces, not solar activity. A geomagnetic storm does not load faults. It does not create new stress. It only determines the timing of ruptures that were going to happen regardless. This would produce a detectable signal in temporal clustering studies, which several have found, but not in cycle-averaged global statistics, and the supporting evidence is no longer thin. A study published in Nature Scientific Reports in 2020 found a statistically significant correlation between solar proton events and increased earthquake probability. The p-value was less than 10 to the negative fifth power. That means the probability of the observed correlation occurring by random chance is less than 1 in 100,000. A study published in AGU Geophysical Research Letters in 2025 by Chen and colleagues documented a century-scale correlation between intense geomagnetic storms and global strong earthquakes. They found statistically significant increases in earthquakes of magnitude 7 or greater following major geomagnetic events. A superposed epoch analysis published in the journal Entropy in 2020 found elevated occurrence of magnitude 7 and above earthquakes in the days following geomagnetic storms using a dataset spanning more than 6 decades. 3 independent studies, 3 different methodologies, 3 different datasets, all pointing in the same direction. When you see convergence like that in science, you pay attention. Any single study can be flawed. Any single dataset can contain hidden biases. But when multiple teams using different approaches arrive at the same conclusion independently, the probability that they are all wrong in the same way starts to get very small. And now, on top of the statistical evidence, there is a physical model from one of the world's leading research universities that explains the mechanism. The statistics said something is happening. The Kyoto model says here is how it could work. The Kyoto model explicitly states that its framework is not designed to forecast individual earthquakes and should not be used for that purpose. What it offers instead is a physical basis for understanding why seismic probability might shift following geomagnetic disturbances. If the model is validated, it would not give us the ability to predict when and where the next earthquake will strike. But it would give us a deeper understanding of the forces acting on fault systems around the world, and that understanding could eventually improve hazard assessments and monitoring strategies. That alone makes it worth taking seriously. And then, 36 hours after a G2 geomagnetic storm, the most stable crust on the planet shakes in one of the quietest places on Earth. Now here is what makes the Uluru earthquake so particularly significant in the context of this model. It is not just any earthquake, it is the exact kind of earthquake that the Kyoto model predicts would produce the most visible signal. On a fault at a plate boundary, the stress perturbation from the ionosphere would be negligible compared to the massive tectonic loading that is already driving the system. The tectonic forces at a subduction zone are measured in hundreds of megapascals. The ionospheric perturbation, even at its strongest, is a few megapascals. At a plate boundary, that is a rounding error. The signal would be lost in the noise. But on a cratonic fault, the situation is completely different. The recurrence interval is measured in tens of thousands of years or longer. The system exists in a state of delicate equilibrium, balanced right at the threshold, where a small perturbation could be the difference between holding and breaking. The tectonic loading is there, but it is spread over a vast area of ancient rock, and the stress on any individual fault may be just barely below the failure threshold. In that situation, a few megapascals of additional stress from the ionospheric electric field could matter. It could be the difference between another century of silence and the fault finally letting go. Whether that is what happened near Uluru on April 4th is something the data cannot definitively tell us. Not yet. Not with a single event. You would need dozens of similar events, carefully catalogued, their timing relative to geomagnetic storms, analysed with the same rigour the supporting studies have already applied to historical data. And that analysis is coming. Researchers around the world are already collecting the data that will eventually test the Kyoto model against reality. The Uluru earthquake will be one data point in that test, but the question has moved from the fringe to the frontier, and the sun, as it turns out, is not done. Part 5. 4 flares in 24 hours. While the geomagnetic storm was settling and the ground was shaking near Uluru, something was happening on the surface of the sun that space weather forecasters had been watching with increasing attention for days. And this part of the story matters not just because of what happened on April 4th, but because of what could happen in the next 72 hours. Active region 4409 sits at approximately north 02, west 15 on the solar disk. That coordinates designation might not mean much to you unless you track solar activity, but the position is crucial. North 02 means it is essentially on the solar equator, slightly north. W15 means it is just west of the centre of the solar disk as seen from Earth. In other words, it is pointed almost directly at us. The position of an active region on the solar disk determines how geo-effective its eruptions can be. A flare or CME from a region on the limb, the edge of the sun as we see it, sends its energy off to the side. It might produce a glancing blow or miss Earth entirely. A flare or CME from a region near disk center sends its energy straight at us. It is the difference between a boxer throwing a punch that clips your shoulder and one that lands square on your jaw. Region 4409 is in the jaw punch position, and it has been throwing punches all day. On April 4th, this region produced 4 M-class solar flares in a single 24-hour period. The largest was an M7.5 at 0117 UTC, which triggered an R2 moderate radio blackout over the Pacific region. Following that were an M1.7 at 0758 UTC, an M1.2 at 1211 UTC, and an M1.0 at 2304 UTC. 4 flares, all from the same region, all in one day. To put that in context, the average daily M-class flare rate during the current solar maximum, which is the most active phase of solar cycle 25, is approximately 0.5 to 1 per day across all active regions on the entire solar disk combined. Region 4409 alone produced 4 times the daily global average. That is sustained magnetic reconnection at a significantly elevated rate. The region itself is substantial, 26 sunspots, an area of 170 millionths of the solar hemisphere, a magnetic classification of beta-gamma, which means its magnetic field has a complex structure with both positive and negative polarity regions intermixed. This kind of configuration stores energy in twisted, stressed magnetic field lines that can snap and reconnect violently, releasing energy as flares. There is a pattern in the April 4th activity that is worth noting. All 4 M-class flares were impulsive. That means they were short-duration events with rapid rise and fall times. None of them produced a coronal mass ejection. This is somewhat unusual for a region of this size and complexity producing flares of this magnitude. What it suggests is that the region is releasing energy in rapid bursts rather than building it up into a single catastrophic event. But here is the thing about solar physics, and this is something that catches a lot of people off guard. The fact that a region has been releasing energy in small bursts does not mean it cannot produce a large eruption. You might think that all those M-class flares are bleeding off pressure, like a pressure valve on a boiler, preventing a catastrophic failure. And sometimes that is exactly what happens. The region flares repeatedly at moderate levels and then gradually decays without ever producing a major event. But other times, the opposite happens. The moderate flares are a sign of increasing magnetic complexity, of field lines twisting and tangling at an accelerating rate, and the big event comes not despite the smaller flares but in addition to them. The M7.5 on April 4th was a significant step up from the M1 to M3 range the region had been producing in previous days. The escalation is notable, and the NOAA Space Weather Prediction Center's forecast reflects the risk. They assign region 4409 an 80% probability of producing C-class flares, a 40% probability of M-class flares, and a 15% probability of X-class flares over the next 24 hours. For the broader disk, SWPC forecasts a 55% chance of R1 to R2 minor to moderate radio blackouts, and a 20% chance of R3 strong radio blackouts from April 5th through 7th. Now, you might hear 15% and think that sounds low. It is not. In space weather forecasting, a 15% X-class probability is a serious alert condition. Most active regions on the Sun have X-class probabilities of 1% or less. 15% means the forecasters at SWPC are looking at the magnetic complexity of this region and seeing configurations that they know, from decades of historical data, have a meaningful chance of producing the most powerful class of solar eruption. 1 in 7 is not small odds when the stakes include global radio blackouts, satellite damage, and potential geomagnetic storms. A 15% chance of an X-class flare from a region at disk center is not something space weather forecasters treat casually. An X-class flare from that position could produce a CME directed squarely at Earth, arriving in 1 to 3 days. Depending on the magnitude and the magnetic orientation of the CME, it could produce a G3, G4, or even G5 geomagnetic storm. And if the Kyoto capacitive coupling model is correct, that storm would open another window of elevated seismic probability on a planet where the ground just shook in one of its quietest places. And there is one more reason why the activity from region 4409 matters right now. One reason that has nothing to do with earthquakes and everything to do with 4 human beings who are currently farther from Earth than any person has been in more than half a century. Part 6. The most exposed humans in history. On April 2nd, 2026, a rocket lifted off from Kennedy Space Center in Florida, carrying 4 astronauts on a trajectory that no human being has flown since December of 1972. The Artemis II mission. NASA's Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen, aboard the Orion spacecraft, heading for a flyby of the Moon. This is the first crewed mission beyond low Earth orbit in 54 years. The last humans to fly this far from Earth were the crew of Apollo 17, Gene Cernan, Ron Evans, and Harrison Schmitt, who orbited and landed on the Moon in December 1972. Every crewed spaceflight since then, every space shuttle mission, every stay on the International Space Station, every Crew Dragon flight has taken place within a few hundred kilometers of Earth's surface, safely nestled inside the protective cocoon of Earth's magnetosphere. Let that sink in. 54 years. An entire generation was born, grew up, went to college, started careers, and had children of their own in the time between the last mission beyond Earth orbit and this one. The entire Space Shuttle program, all 135 missions, happened and ended within that gap. The International Space Station was conceived, designed, launched, assembled, staffed, and has been continuously occupied for over 25 years, all without a single human leaving the neighborhood of low Earth orbit. The magnetosphere is the magnetic bubble that surrounds our planet, generated by the churning of molten iron in the outer core. It deflects the solar wind, traps charged particles in the Van Allen radiation belts, and shields the surface and low Earth orbit from the worst of the Sun's energetic output. Without it, life on Earth's surface would be constantly bombarded by radiation that would strip away the atmosphere and sterilize the ground. The Artemis II crew is now beyond it. In cislunar space, between the Earth and the Moon, there is no magnetosphere. There is no magnetic shield. The astronauts are exposed to the full ambient space radiation environment, which includes galactic cosmic rays, high-energy particles from outside the solar system that are always present, and any solar energetic particle events that occur during the mission. They are, in the most literal sense, unprotected. The M7.5 flare from region 4409 on April 4th produced a measurable spike in the proton flux environment surrounding the spacecraft. The greater than 10 mega-electron-volt proton flux peaked at 3.23 particle flux units. That is below the S1 minor solar radiation storm threshold of 10 particle flux units, but it is measurably above background. The greater than 1 mega-electron-volt channel peaked at 431 particle flux units. The 2 mega-electron-volt electron flux has been continuously elevated above 1,000 particle flux units since April 3rd, peaking at 4,465 on April 4th. Over the course of the 10-day Artemis II mission, the crew is expected to burn through approximately 5% of their lifetime radiation exposure caps. 5% in 10 days. The International Space Station crew typically accumulates that same amount over several months in low Earth orbit, where they have the magnetosphere reducing their exposure. But the real fear is not the background accumulation. 5% over 10 days, while significant, is manageable. The career exposure limits for astronauts are set with long missions in mind. The real fear, the thing that keeps radiation health officers at NASA awake at night during a mission like this, is a single catastrophic event. A solar proton event of sufficient magnitude to deliver an acute radiation dose in hours rather than days. On August 2nd through 11th of 1972, the Sun produced a series of flares that became known as the August 72 solar storm. The largest, called the Seahorse flare for its shape on solar imagery, occurred on August 4th. By pure luck, this sequence fell between Apollo 16, which had returned to Earth in April, and Apollo 17, which would not launch until December. No astronauts were in cislunar space. If they had been, the consequences would have been severe. The radiation dosage for an astronaut outside the spacecraft peaked at 241 rem per hour. Inside the Apollo command module, the rate would have approached 66 rem per hour. Over the duration of a typical lunar round trip, each astronaut would have received a projected cumulative skin dose of approximately 358 rem. At those levels, vomiting and nausea would have set in within hours. Hospitalization for 3 to 6 months would have been likely. And there was an estimated 20% chance that the dose would have been fatal. The Apollo astronauts of that era knew the risk, even if the public didn't fully appreciate it. They flew during a period of relatively low solar activity, and they flew fast. The total time spent beyond the magnetosphere on a lunar mission was roughly 6 to 8 days. They were rolling the dice every time, and they knew it. The August 72 event proved just how loaded those dice were. Now, the Orion spacecraft is significantly better shielded than the Apollo command module. It carries the Hera sensor system, the hybrid electronic radiation assessor, which provides real-time radiation monitoring throughout the cabin. The crew has a radiation shelter protocol that can be activated within 30 minutes, retreating to the most shielded area of the spacecraft and using onboard materials as additional mass shielding. NASA and NOAA's Space Weather Prediction Center are actively monitoring conditions throughout the mission. But the numbers are still sobering. Region 4409 has a 15% probability of producing an X-class flare. It is positioned at disk center. If it produces a CME-associated X-class event, the energetic particles could arrive at the Orion spacecraft within minutes to hours, depending on the particle energy. The Hera system would detect the radiation spike, the crew would retreat to the shelter, and then they would wait, behind a few centimeters of aluminum and polymer shielding, while the storm passed. The mission also benefits from a quirk of lunar orbital mechanics. For approximately 3 to 6 days during the Moon's 28-day orbit, the Moon passes through Earth's magnetotail, the elongated downstream extension of the magnetosphere shaped by the solar wind. During those periods, the radiation environment around the Moon dropped significantly. Whether the Artemis II trajectory intersects with this magneto-tail passage depends on the precise timing, and that timing was one of the factors considered in the mission planning. But no amount of planning can eliminate the fundamental uncertainty. You cannot predict when the sun will fire. You can monitor, you can prepare, you can have protocols. You cannot control a star. Dr. Victor Velasco Herrera of the National Autonomous University of Mexico publicly recommended delaying the Artemis II launch due to solar conditions. He cited analysis suggesting that the risk of extreme radiation exposure was elevated during this period of the solar cycle. NASA proceeded with the launch on schedule. Scientific American published an article in April 2026 titled "Space Weather Could Threaten Artemis II Astronauts," detailing the monitoring protocols and the risk calculus. The same sun that may have just shaken the oldest rock on the planet is pointed directly at 4 people who have no magnetic field between them and whatever it decides to do next. And the region responsible for the M7.5 is still there, still active, still firing. Think about what we are describing here. The same sun, the same star, is simultaneously shaking the crust of the Earth, according to the Kyoto model, firing M-class flares from a disk center active region, and irradiating 4 astronauts who have voluntarily placed themselves beyond the one thing that protects all of us from the full force of our star. The same solar activity is affecting the ground, the sky, and the humans in between. That is not 3 separate stories. That is one story told from 3 angles. If you are watching this video right now, those 4 astronauts are farther from home than any human being has been in your lifetime, flying through the aftermath of a solar storm that hit KP7, with a sun that just produced the largest flare from its most dangerous region while pointed straight at them. That is not a theoretical risk. That is Tuesday. Part 7. When the ground shakes everywhere. The earthquake near Uluru was not the only significant seismic event of the day, not even close. And this is where the story starts to feel less like an isolated event and more like a pattern that demands an explanation. At 10:34 UTC on April 4th, a magnitude 6.0 earthquake struck 90 kilometers southeast of Sarangani in the Philippines at a depth of 99.6 kilometers. This was a deep subduction zone event, the kind of earthquake that occurs regularly along the Philippine Mobile Belt, where the Philippine sea plate grinds against the Eurasian plate. The USGS issued a green alert. Approximately 627,000 people experienced light shaking. No structural damage was reported, no casualties, no tsunami threat. On its own, the Philippines event would be unremarkable. Earthquakes of this magnitude occur along the Philippine subduction zones with a regularity that would be terrifying if anyone paused to think about it. The Philippines sits on what geologists sometimes call the Pacific Ring of Fire, a horseshoe-shaped belt of subduction zones and volcanic arcs that encircles the Pacific Ocean and produces approximately 90% of the world's earthquakes. A magnitude 6 in the Philippines is Tuesday. It barely makes the local news, but it did not occur on its own. It occurred on the same day as the Uluru event, and it occurred in the aftermath of something much larger. 3 days earlier, on April 1st at 22:48 UTC, a magnitude 7.4 earthquake had struck the northern Molucca Sea in Indonesia. That event was serious. It killed 1 person, a 70-year-old woman in a building collapse in Manado City, North Sulawesi. It triggered a tsunami, with waves reaching approximately 75 centimeters, 0.75 meters, at monitoring stations. The Pacific Tsunami Warning Center issued alerts. Indonesia's meteorological agency activated its warning system. The Philippines, Malaysia, Taiwan, and Papua New Guinea were all placed on alert. The Molucca Sea is one of the most tectonically complex environments on Earth. It is the site of 2 subduction zones that face each other, an extremely rare geological configuration where 2 plates are simultaneously diving beneath each other. Imagine 2 conveyor belts facing each other, both running downward at the same time. The material caught between them gets compressed, deformed, and shattered. This double subduction creates a region of extraordinary seismic complexity, one of the most earthquake-prone zones on the entire planet. In the days following the M7.4, the aftershock sequence was relentless. Nearly 50 aftershocks were recorded, including a magnitude 6.2 on April 2nd. And on April 4th, the same day as the Uluru earthquake, 5 more events of magnitude 4.5 or above clustered near Ternate, Indonesia, within hours of each other. Magnitude 4.8, 4.7, 4.6, 4.6 again, and 4.5. All within a tight geographic cluster, all continuing the sequence. Beyond the Molucca Sea, the global seismic picture on April 4th included a magnitude 5.5 near Hualien City, Taiwan, a region that has been consistently active, a magnitude 5.0 at the Kermadec Islands south of New Zealand, and a magnitude 5.0 near Honshu, Japan, both within the expected range for those active boundaries. The total count of magnitude 4.5 and above earthquakes globally over the preceding 7 days was 151. The global average is approximately 15 to 20 per day, which works out to 105 to 140 per week. So 151 is at the upper end of normal but not dramatically outside the expected range. But here is the question that the Kyoto model raises, and it is a question that changes how you look at all of this data. If the capacitive coupling mechanism works at all, it would not selectively target one fault. The ionospheric disturbance from a geomagnetic storm is global. The electric field propagation would affect every critically stressed fault on the planet simultaneously. The Uluru event would not be an isolated triggered event. It would be one visible data point in a planet-wide probability shift. The Molucca Sea swarm, the Philippines earthquake, the Hualien event, the Uluru event, all within the same post-storm window, all on the same day or within days of the G2 storm that peaked on April 3rd. Is that a coincidence? Probably, if you look at each event in isolation. But the Kyoto model does not ask you to look at them in isolation. It asks you to consider whether the background probability of seismic events across the globe ticked upward by some small but measurable amount in the 36 to 72 hours following the storm. Think about it this way. If you flip a coin 10 times and get 7 heads, that could be random. But if someone told you before the flip that the coin was slightly weighted and then you got 7 heads, you would take the weighting claim a lot more seriously. The Kyoto model told us the coin was weighted. Then we got 7 heads. That does not prove the weighting is real, but it means we cannot ignore the possibility, and the history of the Australian craton suggests that when the ground moves there, it is worth paying very close attention to why. Part 8. What history tells us. The earthquake near Uluru on April 4th did not happen in a geological vacuum. Central Australia has a history of intraplate earthquakes, and every single one of them has raised the same fundamental question. What triggered this rupture in this ancient rock at this specific time? Every major intraplate earthquake in the Australian interior has been a surprise. Every single one. And every single one has added a piece to a puzzle that we are still far from completing. The most recent and most dramatic comparison is the Petermann Ranges earthquake of May 21, 2016, a magnitude 6.1 event that struck approximately 150 kilometres southwest of Uluru, in the same general region of the central Australian outback. That earthquake did something that no instrumentally recorded earthquake in Central Australia had done before. It ruptured the surface. Satellite imagery revealed a 21-kilometre long surface rupture cutting across the desert landscape. 21 kilometres. That is 13 miles of the Earth's surface cracking open in a place that had been geologically silent for longer than recorded human history. A scar in the Earth where a fault hidden beneath the surface had suddenly moved. The rupture was a reverse fault, meaning one side of the fault was thrust upward over the other, consistent with the compressive stress regime generated by plate boundary forces being transmitted across the continental interior. But the fault itself was previously unmapped. It was a secondary backthrust of the much larger Woodruff thrust, an ancient geological structure. Nobody knew it was there until it moved. Nobody had modelled it. Nobody had assessed its seismic hazard. The Petermann Ranges earthquake was a wake-up call for Australian seismology. It demonstrated that Central Australia was capable of producing earthquakes large enough to rupture the surface, on faults that were completely unknown to science with virtually no warning. The implications for hazard assessment were significant, and then the research into what triggered it produced a finding that connects directly to the story we are telling today. A study published in Geophysical Research Letters in 2019 examined the Petermann Ranges event and reached a surprising conclusion. The researchers found evidence that changes in groundwater level may have contributed to triggering the earthquake. The region had experienced unusual rainfall patterns in the years preceding the event, and the resulting changes in pore pressure at depth may have been sufficient to reduce the effective stress on the fault and push it toward failure. That finding is significant in the context of the Uluru earthquake and the Kyoto model because it establishes a precedent. External forcing, meaning a force applied to the fault system from outside the tectonic stress regime, can influence when an intraplate earthquake occurs. If changing groundwater levels can do it, the question of whether ionospheric electric fields can do it is not a leap. It is an extension of the same principle. Go back further, January 22nd, 1988, the Tennant Creek earthquake sequence. And this one is genuinely wild. 3 earthquakes, magnitude 6.3, 6.4 and 6.7, struck within 12 hours of each other in the Tennant Creek area of the Northern Territory. Not one major earthquake, 3 in 12 hours, each one larger than the last, as if the earth was clearing its throat and then screaming. The largest, the 6.7, remains the most powerful earthquake ever instrumentally recorded in mainland Australia. The sequence produced approximately 32 kilometres of surface rupture. These were not small, forgettable events. They rearranged the landscape. They cracked the surface of a continent that is not supposed to crack. Consider what that means. 3 major earthquakes in 12 hours in the middle of a continent. The ground literally broke open in a place that has no business breaking open, according to the simplified version of plate tectonics that most people learn in school. There is no plate boundary near Tennant Creek. There is no volcanic arc. There is nothing but old, cold, supposedly dead rock. The Tennant Creek sequence occurred in the Proterozoic North Australian craton, ancient rock that had been sitting undisturbed for over 1 billion years. The faults that ruptured were ancient structures, reactivated by modern tectonic stress transmitted from the plate boundaries thousands of kilometres away. Research published in 2019 described the Tennant Creek sequence as a protracted intraplate multi-main shock sequence that extended from 1987 through 2019, with the main cluster in January 88 representing the catastrophic failure of a fault system that had been building toward rupture for an unknown but potentially vast period of time. Further back still, December the 21st, 1937, a magnitude 6.0 earthquake in the Simpson Desert, southeast of Alice Springs. This event predates modern seismic instrumentation, so the data is limited, but it was widely felt across Central Australia. And in 2012 and 2013, magnitude 5.4 earthquakes were recorded near Ernabella, in the same broad region as the Uluru event. And those are just the events we have instrumental records for. Australia has only had a modern seismic monitoring network since the mid-20th century. Before that, the record is limited to felt reports and geological evidence. There could be dozens of similar events in the past few thousand years that we simply have no record of, because nobody was there to feel them, and no seismograph was there to record them. The outback is vast and empty, and earthquakes that would have made headlines in populated regions can happen there and leave no trace except in the rock itself. The pattern that emerges from this history is clear. Central Australia experiences significant intraplate earthquakes at irregular but not impossibly rare intervals. They occur on unmapped or poorly understood fault structures. They are driven by tectonic stress accumulated over immense timescales, and the triggering mechanism for any specific event is almost never identified with certainty. The Uluru earthquake fits this pattern precisely. A magnitude 5.5 or possibly 6.0 event at 10 kilometres depth on a previously uncharacterised fault in Archean age cratonic rock. The stress was there, the fault was there, the only question is why now? If groundwater changes can trigger an intraplate earthquake in Central Australia, as the 2019 study of the Petermann event suggests, then external forcing on cratonic fault systems is not theoretical. It is established. It has happened before in the same region with documented evidence. The only question is, what forms of external forcing are possible and which ones matter? The Kyoto model simply proposes a different source of external forcing. Instead of water pressure changes from below, it proposes electric field changes from above. Both are forces acting on a system already at the breaking point. And this is where the institutional response gets complicated. Because the organisation most people look to for authoritative statements about earthquakes has a very clear position on the matter, and that position does not include the Sun. Part 9, the USGS says no, the data says maybe. The United States Geological Survey maintains an official position that is unambiguous. There is no proven causal link between solar activity and earthquakes. This position is stated clearly on their website and in their public communications. It is the institutional consensus of the world's most prominent earthquake monitoring agency. And before you dismiss them or accuse them of being close-minded, it is worth understanding why they hold this position, because it is not a dismissal born of ignorance. It is a position held by some of the smartest seismologists on the planet, and they have reasons. The USGS objection is grounded in a specific and legitimate scientific argument. If solar activity were a significant driver of earthquake occurrence, they argue, we should see a variation in earthquake frequency that follows the 11-year solar cycle. During solar maximum, when the sun is most active and geomagnetic storms are most frequent and intense, there should be more earthquakes. During solar minimum, when the sun is quiet, there should be fewer. The data does not show this pattern. Global earthquake occurrence does not rise and fall with the solar cycle. Therefore, the conclusion is that solar activity is not a significant factor in earthquake generation. This is a valid objection. It is logical, it is testable, and it is grounded in data. And for most of the history of this debate, it was sufficient to close the conversation. If the signal is not there in the most obvious place to look for it, then the phenomenon probably does not exist. Researchers who proposed solar seismic connections were politely but firmly shown this data, and the conversation ended. For decades, that was the wall. Every attempt to link solar activity to earthquakes crashed against the absence of an 11-year cyclical signal in global seismicity. But science does not just ask whether a signal exists in one specific form. It asks whether there might be other forms the signal could take that have not been tested yet. And the Kyoto capacitive coupling model provides exactly that alternative form. Its explanation for why the cyclical signature is absent is specific, quantitative, and subtle enough that it cannot be dismissed with a wave of the hand. The model does not propose that solar activity drives earthquake occurrence in a bulk statistical sense. It proposes that geomagnetic storms can influence the timing of individual events on faults that are already at or near critical stress. The key word is timing. Not generation, not causation in the broad sense, timing. The model says the sun does not create earthquakes. It says the sun can determine when an earthquake that was going to happen anyway finally happens. Under this model, the total number of earthquakes over a solar cycle would not change, because the earthquakes were going to happen regardless. The tectonic forces are what load the faults. The solar perturbation only determines the specific hour or day that the fault fails. If you average over an entire solar cycle, the effect washes out. The total count is the same. The distribution in time shifts slightly, clustering more in the days following storms, but the aggregate statistics remain unchanged. This is why temporal clustering studies can find a signal that cycle average studies miss. The signal is not in how many earthquakes happen per year or per decade. The signal is in when they happen relative to geomagnetic storms. Look at the wrong timescale and you see nothing. Look at the right timescale, days rather than years, and the pattern appears. Multiple studies have found exactly that signal, but here is where it gets uncomfortable for the institutional position. The Nature Scientific Reports paper from 2020 analysed the temporal relationship between solar proton events and earthquakes, and found a statistically significant correlation with a p-value of less than 10 to the negative fifth power. That is science speak for a 1 in 100,000 probability that the observed pattern is due to random chance. In most fields of science, a p-value that's small would be considered strong evidence. In pharmaceutical trials, a p-value that low would be grounds for approving a drug. In physics, it would prompt a dedicated experimental program. In seismology, apparently it prompts a shrug. The AGU Geophysical Research Letters paper by Chen and colleagues in 2025 examined over a century of data and found statistically significant increases in global strong earthquakes, magnitude 7 and above, following intense geomagnetic storms. This is not a fringe journal. A GU is the American Geophysical Union, one of the most prestigious scientific organizations in earth science. The entropy paper from 2020 used superposed epoch analysis, a technique that aligns multiple events to a common reference point and averages them, to show elevated occurrence of large earthquakes in the days following geomagnetic storms. 3 different teams, 3 different methods, 3 different datasets, all converging on the same conclusion. There is a temporal correlation between geomagnetic disturbances and seismic activity, concentrated in the days immediately following storms, and there is more. A study published in Science Direct in 2025 by a separate team analysed the influence of geomagnetic storms on global main shock earthquake occurrence through the lens of solar wind parameters. They found that certain solar wind conditions, particularly sustained periods of southward-oriented interplanetary magnetic field, correlated with increased seismic activity. The southward orientation is the same condition that makes geomagnetic coupling most efficient, the same condition that turns a moderate solar wind impact into a major geomagnetic storm. Now, correlation is not causation. That statement is the foundation of rigorous science, and it applies here. But correlation combined with a plausible physical mechanism is how causation is eventually established. You observe the pattern, then you find the mechanism that explains it. Newton observed the pattern of falling objects before he described the mechanism of gravity. Darwin observed the pattern of species variation before he described natural selection. Einstein observed the pattern of light's constant speed before he described relativity. In every case, the pattern came first. The mechanism followed. That is how science works. You see something that does not fit the existing model, and then you build a new model that explains it. The Kyoto model provides the mechanism. The statistical studies provide the pattern. The Uluru earthquake provides a data point that fits both. This does not mean the case is closed, far from it. The USGS position remains the institutional consensus, and consensus in science changes slowly. It requires replication, independent verification, rigorous testing, and time. The evidence is building, but it has not yet reached the threshold where the establishment shifts its stance. What we have is a frontier, an active zone of scientific inquiry where the old certainties are being challenged by new data and new models. And at the frontier, the most honest thing anyone can say is that we do not know yet, but we are closer to knowing than we have ever been. The Kyoto paper has been out for 2 months. It has not been debunked. It has not been retracted. It has been cited by subsequent work. The mechanism it proposes is physically consistent with known principles of electrostatics, and the event it predicts, a triggered earthquake within a specific time window following a geomagnetic storm, may have just occurred in the most visible possible location. The next few years of data will tell us whether the Kyoto model survives or falls. But right now, in April 2026, it is very much alive. And whenever there is uncertainty at this scale, whenever established science and emerging evidence point in different directions, there are always people who step into the gap with explanations of their own. Some of those explanations are creative, some are provocative, and some of them, despite being wrong, point at something real. Part 10. The conspiracy layer. Whenever the sun does something dramatic and the Earth responds in a way that seems too perfectly timed, the same names come up in the same conversations. It is as predictable as the sunrise itself. Let me walk you through the claims that are already circulating and will continue to circulate in the days ahead, and let me show you why the real science is both more interesting and more important than any of them. The first and loudest claim will be about HAARP, the High Frequency Active Auroral Research Program, a scientific facility in Gacona, Alaska, designed to study the ionosphere by transmitting high-frequency radio waves into the upper atmosphere. HAARP has been the subject of conspiracy theories since the 1990s, accused of everything from controlling the weather to triggering earthquakes to manipulating human thought. The temporal correlation between the G2 geomagnetic storm and the Uluru earthquake will absolutely be cited as evidence that HAARP, or some equivalent directed energy system, deliberately triggered the quake. Here is the problem with that claim, and it is a problem of scale so enormous that it should end the conversation immediately, though it never does. HAARP's effective radiated power is approximately 3.6 megawatts. That sounds like a lot until you compare it to the energy deposited into the ionosphere by a natural geomagnetic storm, which is measured in terawatts. A terawatt is 1,000,000 megawatts. The geomagnetic storm that hit on April 3rd delivered something on the order of 1,000,000 times more energy to the ionosphere than HAARP could produce at maximum output. If the Kyoto capacitive coupling model is correct, and ionospheric disturbances can influence seismic activity, then the mechanism is driven by the natural storm. not by a research facility in Alaska. HAARP is a candle in a forest fire. It is like accusing someone of causing a hurricane by blowing on a pinwheel. The scales are so mismatched that the comparison is meaningless, and yet this claim will be made, loudly and repeatedly, in comment sections and forum posts and viral threads, because it sounds scary, and because most people do not intuitively grasp the difference between megawatts and terawatts. Now you do. The second claim will be about Uluru itself. Uluru holds extraordinary spiritual significance to the Anangu people, who have been its custodians for tens of thousands of years. In broader New Age and alternative spirituality communities, Uluru is often described as one of the Earth's energy centres, or chakra points, a place where the planet's spiritual energy is concentrated. An earthquake near Uluru will be interpreted by some as an energetic awakening, a signal from the Earth itself, a response to cosmic forces that science cannot measure. There is no scientific basis for the concept of Earth energy centres or planetary chakras, but there is an important distinction between respecting the cultural significance of a place and treating that significance as a scientific explanation. Uluru is culturally sacred. It is geologically remarkable. These are not the same statement, and treating them as interchangeable does a disservice to both the science and the culture. The Anangu people have been custodians of this land for at least 30,000 years, possibly far longer. Their relationship with Uluru is cultural, spiritual, and deeply personal. It is not a data point in someone else's theory about energy grids, and we should be careful about how we frame an earthquake near a sacred site, because the people for whom this site matters most deserve to have their land discussed with respect, not used as a prop for viral speculation. The third claim, and arguably the most insidious, is the idea that the solar seismic connection is suppressed knowledge. That the USGS and other institutions know that the sun triggers earthquakes and are deliberately hiding this information from the public. The gap between the USGS's official position, no proven link, and the growing body of peer-reviewed research suggesting correlation creates a narrative vacuum that conspiracy communities fill with allegations of institutional cover-up. The reality is much less dramatic and much more frustrating. Scientific consensus changes slowly. It requires extraordinary evidence to overturn established positions, and it should. The cost of changing your mind prematurely in science is high. If the USGS announced tomorrow that solar storms trigger earthquakes, and it turned out to be wrong, the credibility damage would be immense. Institutions are conservative by design, and that conservatism, while maddening at the frontier, is what makes their pronouncements trustworthy in the long run. The Kyoto model has been published for 2 months. The supporting studies span only a few years of serious investigation. The evidence needs to accumulate further. More events like the Uluru earthquake need to be studied. More statistical analyses need to be run. The model's predictions need to be tested against future data. This is how science works. It is not a cover-up. It is caution. And if you think about it, the fact that these papers are being published in prestigious journals and discussed openly in the scientific press is the opposite of suppression. The conversation is happening. It is just happening at the speed of science rather than the speed of social media. The fourth claim that will circulate concerns the Artemis 2 crew, the idea that NASA is minimizing or hiding the true radiation risk to the astronauts. The data does not support this allegation. The radiation monitoring systems aboard Orion are sophisticated, and their data feeds are shared with mission control in real time. Scientific American and other major publications have published detailed articles about the radiation risk during this solar maximum period. The question is not whether NASA is hiding the risk. The question is whether their risk assessment adequately accounts for the tail-end probability, the 15% X-class flare chance from a disk center region during the most exposed phase of the mission. That is a legitimate question about risk tolerance, not about cover-up. Here is what I want you to take away from this section. Skepticism of institutions is healthy. Questioning official positions is how science advances, but there is a difference between productive skepticism and conspiratorial thinking. Productive skepticism says, show me the data, explain the mechanism, let me see the peer review. Conspiratorial thinking says they already know, and they are hiding it. One leads to understanding, the other leads to a dead end. And here is the deeper point that gets lost in all of this noise. The real story, the Kyoto capacitive coupling model, is more interesting than any conspiracy theory. It is real scientists doing real work with real data, publishing in real journals, proposing a mechanism that, if confirmed, would fundamentally change our understanding of how the Earth's systems are connected. The conspiracy theories are a distraction from the actual frontier. The truth is not being hidden, it is being investigated, and the investigation is far more compelling than any cover-up narrative could ever be. Part 11. The machine built to answer this. In 4 days, on April 9, 2026, a rocket will lift off from the Guiana Space Center in French Guiana, carrying a satellite that was designed to study exactly the phenomenon at the center of this entire story. The satellite is called SMILE, Solar Wind Magnetosphere Ionosphere Link Explorer. It is a joint mission between the European Space Agency and the Chinese Academy of Sciences. It will ride a Vega C rocket into an orbit that takes it 121,000 kilometers above the North Pole to observe, then dives down to 5,000 kilometers above the South Pole to transmit its data back to ground stations. For its entire history, humanity has studied the magnetosphere indirectly, by measuring magnetic field fluctuations on the ground, by tracking charged particle fluxes with satellites passing through it, by modelling it mathematically. We have never actually seen it. Not in the way you can see a hurricane from space, or watch a volcanic eruption on a satellite feed. The magnetosphere has been invisible. SMILE is about to change that. It will be the first mission in history to observe Earth's magnetosphere in X-ray light. Using a technique based on solar wind charge exchange, where charged particles from the solar wind interact with neutral atoms in Earth's upper atmosphere and emit X-rays, the satellite will produce what amounts to the first movies of the magnetosphere being compressed, deformed, and reshaped by the solar wind in real time. This is not an abstract scientific curiosity. The magnetosphere is the first line of defense between the solar wind and everything beneath it, the ionosphere, the atmosphere, and the crust. The Kyoto capacitive coupling model describes a chain of events that begins with the solar wind disturbing the magnetosphere, which disturbs the ionosphere, which generates electric fields that propagate into the crust. SMILE is designed to observe the first link in that chain with unprecedented detail. If the Kyoto model is correct, and if geomagnetic storms really can influence seismic activity through ionospheric coupling, then SMILE will provide data that could help quantify the relationship. By showing exactly how and where the magnetosphere deforms under solar wind pressure, it will constrain the models that predict how that deformation translates into ionospheric disturbance. Better magnetospheric data means better ionospheric models means better predictions of the electric field propagation the Kyoto team describes. The timing is almost poetic. A satellite built to study the connection between the Sun and the Earth's magnetic environment, launching into a solar maximum, 4 days after an earthquake that may or may not have been influenced by that very connection. The question at the heart of this story, when the Sun erupts, does the ground feel it, may eventually be answered in part by the data SMILE collects. Part 12. The water is rising. While the Sun is firing, the ground is shaking, and astronauts are flying beyond the magnetosphere, there is one more system under stress that rounds out the picture of what is happening on Earth right now. As of April 5, 2026, 100 flood warnings are active across the United States, out of 319 total National Weather Service alerts. That is nearly a third of all active weather alerts in the country dedicated to a single hazard: water. Wisconsin is the epicenter. The Embarrass River near the town of Embarrass and the Wolf River near Shiocton are both approaching the flood of record. Not just flooding. Approaching records. The Wolf River is expected to crest at 11.9 feet, against a flood stage of 11 feet. City parks and agricultural lowlands are going under. The Wabash River Basin, spanning Indiana and Illinois, is experiencing widespread flooding from multiple rounds of rainfall, with warnings extended through April 12th. Rivers across Texas, including the Trinity at Dallas and Denton Creek and the Cowleach Fork of the Sabine River, are in flood as well. And a wild temperature swing is about to hit the central United States that would be the lead story on any normal week. Record warmth in the mid-Atlantic with temperatures well into the 80s. Fahrenheit in early April, a good 20 to 30 degrees above normal for the date, is about to be slammed by a cold air surge that will bring below freezing daytime temperatures to the northern plains and upper Great Lakes by Monday. We are talking about a temperature drop of 50 to 60 degrees Fahrenheit in some locations over the span of 48 hours. That kind of atmospheric whiplash stresses infrastructure, agriculture, and human health in ways that are hard to quantify until you are in the middle of it. Now, I am not going to sit here and tell you the flooding is connected to the geomagnetic storm. That would be irresponsible, and the data does not support it. This is not directly connected to the solar seismic story in any mechanistic way. The flooding is driven by atmospheric dynamics, rainfall patterns, and snowmelt. But it is part of the broader picture. Multiple Earth systems are under stress simultaneously. The sun is active. The ground is moving. The rivers are rising. The atmosphere is oscillating between extremes. Whether these are connected or coincidental is, in a sense, the overarching question of everything we have been talking about. How coupled are the systems? How interconnected is the machine? The Kyoto model suggests the coupling runs deeper than we thought. The flooding suggests the atmosphere has its own stress factors, and on April 5, 2026, all of it is happening at once. Part 13. What happens? Next region. 4409 is still there. It is still firing. The beta-gamma magnetic configuration has not simplified. The NOAA Space Weather Prediction Center maintains a 15% probability of X-class flares over the next 24 hours and a 40% probability of additional M-class events. The 55% chance of R1 to R2 radio blackouts and the 20% chance of R3 strong blackouts will persist through at least April 7th. The next few days are going to be critical on multiple fronts, and every single one of them connects back to the central question of this entire video. If region 4409 produces a CME-associated flare while it remains at or near disk center, the resulting coronal mass ejection would travel directly toward Earth. Depending on the speed of the CME and the orientation of its magnetic field, it could arrive in 1 to 3 days and produce a geomagnetic storm potentially more intense than the G2 on April 3rd. A fast CME from an X-class flare can travel at 2,000 km per second or more, reaching Earth in under 24 hours. A slower one might take 3 days. But the key variable is the magnetic orientation. If the CME arrives with its magnetic field pointed southward, opposite to Earth's field, the coupling will be efficient, the energy transfer will be massive, and the resulting storm could be severe. G3, G4, possibly G5, the kind of storm that makes the news and keeps power grid operators awake all night. If the Kyoto model is correct, that storm would open another window of elevated seismic probability, and it would do so while the ground near Uluru may still be adjusting to whatever happened on April 4th. The Artemis 2 crew has days remaining in cislunar space. Every hour beyond the magnetosphere is an hour of exposure. The HERA sensors are monitoring. The shelter protocol is ready. But the crew cannot come home faster than orbital mechanics allows. They are on a trajectory that was set before launch, and while minor adjustments are possible, the fundamental timeline is fixed. They will fly around the moon and return to Earth when the physics of their orbit dictates, not when the sun decides to cooperate. Now let us talk about the ground, because the story there is not over either. The aftershock situation near Uluru will evolve over the coming days and weeks. Aftershocks typically decrease in frequency and magnitude over time, following a well-understood decay pattern called Amori's law. But as with everything in intraplate seismology, the rules are less certain than they are at plate boundaries. The fault that ruptured is ancient and poorly characterized. The stress state in the surrounding crust is not well constrained. A larger aftershock, while unlikely, cannot be completely ruled out. The Molucca Sea sequence continues in the background. 5 events of magnitude 4.5 or above on April 4th alone, following the magnitude 7.4 on April 1st that triggered the tsunami. That region will remain seismically active for weeks to months as the stress redistributes. The Philippine Sea Plate and the Eurasian Plate are not done arguing. In 4 days, SMILE launches. The satellite will take months to reach its operational orbit and begin returning science data, so it will not provide immediate answers. But it represents the next generation of tools for understanding the Sun-Earth connection. If the capacitive coupling mechanism is real, SMILE's X-ray observations of the magnetosphere will be one piece of the puzzle that helps confirm or refute it. On the volcanic front, Kilauea in Hawaii and Great Sitkin in the Aleutian Islands of Alaska remain at watch and orange alert levels respectively. Kilauea has been in a state of heightened unrest, with elevated seismicity and ground deformation, suggesting magma movement beneath the surface. Great Sitkin has been producing periodic ash emissions. Neither is in immediate crisis, but both are reminders that the Earth's interior is dynamic on multiple fronts simultaneously. The same planet that is being rattled by intraplate earthquakes and pounded by solar storms also has magma chambers that are pressurizing, and volcanic systems that are deciding whether or not to erupt. It is all happening at once because it is always happening at once. We just do not always pay attention. There is something humbling about watching all of this unfold simultaneously. We live on a planet that orbits a star that occasionally throws tantrums. Our planet has a magnetic shield that absorbs most of the punishment. Beneath the shield, the atmosphere moves and the water flows and the crust groans under the weight of forces that have been building since before our species existed. We have built a civilization on top of all of this, and most of the time we forget that any of it is happening. Then a week like this one comes along and you remember. ENSO, the El Niño Southern Oscillation, remains in a neutral state with a trend toward warmer conditions. The Oceanic Nino Index sits at negative 0.16, close to the threshold of La Niña conditions but not crossing it. The coming months will determine whether the tropical Pacific shifts into El Niño, which would reshape global weather patterns and add another variable to the already complex picture of Earth system interactions. And the 100 flood warnings across the United States will persist through the week as rivers continue to crest. The Embarrass River and the Wolf River in Wisconsin will rise, potentially to or past their records. The cold surge arriving by Monday will freeze the ground in the northern plains while the rivers are still swollen, creating a new set of hazards. Step back for a moment and look at the full picture. All of this is happening at once. The sun is firing from a region pointed directly at Earth. Astronauts are flying beyond the magnetic shield. The ground moved in one of the quietest places on the planet, 36 hours after a geomagnetic storm, within the window that a model published 2 months ago predicted. Rivers are approaching record levels. A satellite designed to study the Sun-Earth connection launches in days. I want you to hold this picture in your mind for a moment. All of it, simultaneously. Because this is not a series of unrelated stories. This is what it looks like when you zoom out far enough to see the whole system at once. Most of the time, we cover these stories individually. The earthquake story, the space weather story, the flooding story, the space mission story. We treat them as separate beats in separate news cycles, but they are not separate. They are different expressions of the same interconnected planetary and solar system. The question that ties all of this together is deceptively simple. How connected is the system? When the sun erupts, does the ionosphere flinch? When the ionosphere flinches, does the crust feel it? When the crust moves, is it responding to something 93 million miles away? Or is the timing just coincidence? The Kyoto model says the coupling is real. The USGS says the evidence is not yet sufficient. The data says something is going on, but the jury is still out. And the universe does not care about the jury. It just does what it does. On April 4th, 2026, a fault in the Australian craton moved. That fault has been there for longer than complex life has existed on this planet. It has survived ice ages and supercontinent cycles and extinction events that wiped out 96% of all species. And on one specific day, in one specific hour, it moved. Not because the rock was weak, not because the stress was new. The tectonic forces had been building for millennia. Everything about this fault said stability. Everything about this rock said permanence. And then it moved. Something tipped the balance. Something, on April 4th, 2026, said now. Maybe that something was purely geological. Maybe the stress finally reached a threshold that had been approaching for 10,000 years and the timing was random. Maybe the geomagnetic storm had nothing to do with it. That is possible. That might even be the most likely explanation in any given individual case. But maybe it was the storm. Maybe the electric field from the ionospheric disturbance reached down through the atmosphere and into the fractured, water-saturated rock at 10 kilometers depth and added the final increment of stress that the fault needed to fail. Maybe the sun reached across 93 million miles of vacuum and shook the Earth. And maybe that sounds impossible until you read the Kyoto paper and realize the physics actually works. Was it the sun? We do not know. That is the honest answer. And I know that is frustrating. You have watched this far, and you want a definitive answer. You want someone to tell you yes, the geomagnetic storm triggered the earthquake, or no, it was pure coincidence and you can move on with your day. But the universe does not owe us certainty. And that honest answer, that refusal to pretend we have certainty where none exists, is what separates science from everything else. The conspiracy theorists are certain, the debunkers are certain. The researchers at Kyoto University are the ones saying maybe, here is our model, here are our numbers, test it. That is the frontier. That is where the interesting work happens, not in certainty, but in the space between what we know and what we are about to find out. 4 astronauts are flying around the moon tonight. The sun is pointed at them, and the oldest rock on Earth just reminded us that even the most stable things can move when something pushes them hard enough. Whether the push came from below or from above is the question of the hour. And the answer, when it comes, will change how we understand the planet we live on. It will change how we think about risk, how we prepare for earthquakes, how we monitor the sun, how we plan missions beyond the magnetosphere, how we build power grids and design satellites and protect the infrastructure that modern civilization depends on. Because if the systems are coupled, if the sun's tantrums really do ripple through the magnetosphere and the ionosphere and into the crust, then we have been treating each of these domains as separate problems when they are actually one interconnected machine. The Kyoto team proposed the coupling. The statistical studies found the signal. The Uluru earthquake provided a data point. SMILE will provide the observation platform. And in the coming months and years, we will find out whether this is the beginning of a paradigm shift or a false alarm. Either way, the question was worth asking. And either way, 4 astronauts are still flying around the moon tonight, the sun is still firing, and the oldest rock on Earth just reminded every one of us that nothing is as permanent as it looks. We will be here when the next chapter of this story unfolds. Tomorrow, Region 4409 will still be there. The Artemis crew will still be flying. The rivers will still be rising. And somewhere beneath the surface of this planet, ancient faults are sitting at the edge of failure, loaded by forces that have been building since before our species existed, waiting for something to tip the balance. Whether that something comes from below or from above, or from some combination of the two that we have not yet imagined, is the question that will define the next era of Earth science. And I have a feeling the answer is going to unfold sooner than anyone expects.